Okay? So I'm going to ask y'all, and I want someone else to get in on the conversation. When we ask about the mean, are we talking about the height, or are we kind of more focused on what Emma's saying about, because you're looking here, I think, Emma, right at the center of that histogram?
I mean, yeah.
That's how you identified the mean?
But also just like looking at the peak. Yeah, and then just like going down like the big yeah.
Okay. But I'm talking about like, so you're, Melbourne is talking about the heights are all the same, right? The height being all the same, does that tell me about the mean?
No.
So we want to pay attention and learn from it. What does the height all being the same tell us about? The variability, the spread. Remember, for it to get to the same height, that means it's the same amount of compactness around the mean. That tells us about our spread. So notice the mean is a measure of what again? Measure of center. So notice how I literally just go to the center of those histograms. And if I look at it as a number line, would this number right here be higher than the other two measures of center?
Yes.
Yes. So F has the highest.
What?
For real?
If that's the highest?
I mean, if you look right here, highest measure of center.
Oh, okay.
If you look at the center of that graph, isn't it the highest one?
No, I have a great part.
Okay. So F has the highest measure of center. I'm going to put in parentheses mean. Then
with a woman on it.
E,
Maya Angelou.
and then D.
That's Maya Angelou.
Wait, so this whole, they got the same peak thing would be for standard deviation?
Ah, the same height would be all about that spread, that standard deviation. Oh, man, I forgot to do this. I never need to do the attendance. I'm going to set an alarm for myself every single day. I'm just going to set an alarm on my phone now. Thank you.
Attendance.
Alright.
One of the girls just came back.
I know, adore me for like just focusing on teaching my students. I'm the worst.
He has a wife. What are you
As
talking
soon
about?
as they call, who's missing? I wrote it down in my book, but
Go ahead,
Max.
hurry up. Go ahead, hurry up. Pick that up.
No one's missing besides Max, right? Okay.
What is the running thing mean?
So do you actually get like strikes or something if you don't turn it in? No.
I think
Oh,
Sorry.
I see like a dress.
yeah, I think.
Wait. Okay, so look at the centers of the graph on number line.
What if we already wrote that, but just in a shorter way?
Do you have the ideas?
Yes.
Okay.
Okay. Still all be symmetrical.
Well, does symmetry actually matter for me?
Probably most likely not.
No. Symmetry doesn't matter that much. There's some things that ties into, but it's not what we're focused on. Okay. Compare the standard deviation of each distribution. So the standard deviations are all the same. They have the same height. They have the same width, right? Well, remember, does the shape define the standard deviation? Remember, shape is something different. Standard deviation is a measure of spread, right?
Yeah.
So all distributions have the same height and I will make this note, and width. I will say that height is not the only thing that matters. I'll show you why in a second. So make that note.
We really got 20 minutes left. This would be a long week.
So I want you to note those two graphs right there, those two roughly normal distributions. They have roughly the same height, correct? But if they're on the same number line, which one has more variability, more spread?
The one on the right.
So it's not just the height, it's also the width, okay? It's both of those factors together. All right. I want you to individually do talk the talk. I'm going to have you turn it in so I can reflect on how well we are prepared for this. So make sure you put your name at the top. I'm going to give you all, I'm going to say 6 minutes. We'll see where we are after that. But do that talk the talk on this page independently because I need to see where you are, not just your group.
Can I have a Band-Aid?
We're on that bookcase. Madison, come on. Y'all have 6 minutes. Let's go. Yeah, do the talk the talk. No, you have 6 minutes to get done. Time to do some math. What statistics? Guys, stop talking. Get to work. Pick up the pencil and do something. Do something now. I didn't ask. I need you to work.
Do some.
Let me say it this way. I'll say this. You have 5 minutes to get it done in class. You don't get it done in class, you're doing it for homework.
Okay, but I gotta go to work today and.
Well,
Every class.
they're on the supplemental sheet, but I would just look at those. Those types of curves are in the book. How would we describe those curves?
Could be me.
Key Anthony.
I'm sorry.
Hush. Kai, think you were talking to. Stop it. Just do the talk. Okay. Sweeta.
I'm science plus symmetrical.
I didn't ask. If she needs to misspell it, she can misspell it. I just need to see ideas. Once you finish your talk the talk, go ahead and carefully rip that sheet of paper out, and I will collect it. Make sure your name's on the back side. So like next to where it says talk the talk, next to where it says talk the talk, put your name there.
messing with my life?
90 more seconds to get it done.
I play with my pocket knife a lot. It's not based on the game.
Okay.
How y'all with y'all's outside videos?
Because I take the time.
We called you always been on the
I didn't
Say again.
know.
We called you about keeping
Keep it open. We're going to the next lesson.
Golly.
Guys, you can go and flip in your book to the next lesson. Did you already give me yours?
Well, we're supposed to do the
Did you already give me yours?
Yeah, we're supposed to do the back.
That's right. What?
You wanted us to do this, right?
Yes, the practice. Those top two, D and E, go with the previous page. They go with number 2 on the previous page.
Okay.
Yeah.
We supposed to keep this, right?
All right, time's up. Tear it out, turn it in. If you're not done, you gotta finish it for homework or finish it during enrichment and bring it back to me today. You better be quick. I'm about to go. I'm about to motor. All right, whose do I not have yet? Owen, Jackson, name on there. Yep.
I need a definition. Oh,
Say
I
again.
thought you were supposed to do 1 and 2.
you know what I'm doing? I'm gonna
You're gonna hold on to yours till like 30.
You right?
All right.
I'm so excited for today.
I am moving forward, going further into the lesson, or the next lesson. So what we're about to study, again, if you have not finished this, if you want to bring it back to me during enrichment, you can, or after enrichment. Or if you need to bring it back tomorrow, you can do that. We're going to learn about something called the empirical rule to estimate probabilities of events. This is something that only works when we have a normal distribution, right? So be aware of that. This is one of the reasons why we need normal distributions. And so it's called, the lesson is the form of norm, empirical rule for normal distributions. We should be able to wrap this up hopefully tomorrow pretty quickly. So here's what we're looking at. All right, this is where, yes ma'am.
Okay.
M4 or M5
19.
thank you. Yeah, it's just the very next lesson in the book. And then we're on to getting started. There we go. So anybody recognize these curves?
What do you mean? Oh, they're the same from the previous.
These are the same from the previous lesson, the E phone and unlimited when we had 10,000 phones. That's the same curves. Notice some of us were wondering about the gaps or things like that. Notice we're just going to approximate it with a smooth curve here. All right. This is also where standard deviation comes into play and what I want you to pay attention to. Notice right here it says the norm, well, first off, relative frequency histograms are shown. The normal curves for each data set are mapped on top. So notice, does this perfectly hit that data?
No.
No, but we're going to say that the data is approximately normal or roughly normal, just like how we talked about it being roughly symmetric, right? And so when it is approximately normal, we're going to be able to use something called the empirical rule, which we need to learn about. So right here, though, I want to point this out to you. Normal curves can be graphed with units of standard deviation on the horizontal axis. The normal curve for the E-phone sample has a standard deviation of 0.5 hours. Do not forget what that means. Can anyone explain to us what it means for the E-phone sample to have a standard deviation of 0.5 hours?
We must have talked about D yesterday.
We did.
True.
When we did the calculations of standard deviation?
Was I here?
Yes.
Oh, dang.
I think Max is the only one who was not here. So let me remind you, this is why we did all those calculations. Well, we eventually used it there, but I think previously we wrote notes and a table on page M5-10 Someone's wrote in a separate notebook paper. What did we say standard deviation is?
Typically how far back is from the mean.
Oh no, sorry. Let's let people volunteer. That was my bad on that. I will say Tori was the first one with her hand up, so I'll let her say it first. Okay, it has something to do with space away from the mean. Can we get someone else to add on to it? Kaya, just because she had her hand up earlier.
Typically, well, standard is typically how far the values differ from the mean.
So typical standard deviation, a typical amount. Remember, I also said that that's an average, right? A typical amount that the values differ from the mean. That's really what it is. So when I say that the standard deviation is 0.5 hours, that means that a typical amount that the data deviates from the mean is what? 0.5 hours. And so when we're looking here, we have unlimited sample has a standard deviation of 0.4. So for the unlimited, a typical amount that the data deviates from the mean is 0.4 hours. That's a typical amount that it deviates by. And so I will point this out. What should we notice about the height of unlimited, especially in relation to the standard deviation?
The peak is slightly higher.
The peak is slightly higher. The data is a little bit more compressed because it has less variability, less spread. It has a smaller standard deviation. Okay, so the mean of each sample is 10 hours. And so the normal curve for the battery life of each cell phone is given. For each standard deviation shown, label the corresponding battery life in hours. Well, if you have 0 standard deviations, what are you looking at?
A straight line?
Yes, but remember, so 1 standard deviation, notice how it's a positive 1? That means it's 1 standard deviation more than what?
More than
More than the mean, right? Standard deviations are in respect to the mean. So if we have 0 standard deviations, what are we looking at? The mean. 0 standard deviations equals the mean, right? So what they're saying here is if I look at this 0, what is the value in hours of battery life? It's the mean, so it is.
0?
What was the mean? So remember, this is 0 standard deviations. But we just said 0 standard deviations is the mean. What was the mean battery life for these cell phones?
0.5.
10 hours.
Say it again, AJ.
10 hours.
10 hours.
I said that.
I didn't hear you, Madison. I'm sorry. But what was 0.5? That was the standard deviation. So 0 standard deviations above or below the mean, that's 10 hours. What's 1 standard deviation above the mean then?
11?
What was your standard deviation?
10.5. 10.5.
10.
Because the standard deviation was 0.5. So one's Madison, it literally defines it up here. Bam! 0.5, okay? So 1 standard deviation above the mean, you would add that 0.5, so 10.5.
That's what I just said.
Yeah,
that is
Did
what
I ever
just
say
said.
you were wrong?
You did it. I'm sorry.
Okay. 2 standard deviations above the mean.
11.
11.
It'd be another half an hour more. 3 standard deviations above the mean.
11.5.
Wait, so Mr. King, so if we look to the middle, we subtract 0.5?
There we go, right? Notice this is 1 standard deviation below the mean, so we're going to subtract that 0.5 and get, and, right? So when it's a positive, it indicates that standard deviation is above the mean. Negative indicates that it is, bless you. When it's negative, it's below the mean, right? So again here, 0, what is that?
10?
It is 10 again, right? They have the same mean. 1 standard deviation above the mean.
10.5?
No, 10.4.
Remember, it's 0.4 now for unlimited.
Come on,
Then
7.8. 7.8.
11.2.
11.2.
Where did you get 7.8 from?
Remember, you're adding how much each time for the standard deviations?
0.4.
0.4. And then when we go to the negatives,
9.6.
Because if it's a negative, it's below the mean, meaning that we are going to subtract
9.2.
Yeah, no.
8.8.
8.8.
Slow down. You know what I'm saying?
Okay?
Not
So, negative equals standard deviation below mean. Positives equals standard deviations above mean.
What they say under negative?
SD, standard deviations below mean. Okay? And so we just want to recognize that if it's standard deviation, if it's negative standard deviations, we're talking about below the mean. And so here it has us interpreting what is the meaning of S equals 0. That's this part right here. The number of standard deviations is 0, that's the what? Mean. So when, and I would say SD, I don't like when S equals 0. When SD equals 0, we are looking at the mean, but don't forget we always want context. What is the mean referring to? It is the middle, but the context. Average of what?
The battery life.
The battery life. Remember, these numbers are all about the battery lives of these phones. So looking at the mean battery life of cell phones. All right.
Mr. Kenny, can I be honest with you?
No, man, never. I don't want you to be honest.
But it's not. But it's not bad.
Just kidding. I'm trolling you.
Oh,
No.
oh, he said I'm trolling. You know, he definitely. Never mind. We're not gonna ever use this in the future. Are we?
That's not true.
Okay, but when will you most use this? Like,
So you would be surprised, like you would never have noticed it before because you weren't aware of it, but anytime you look at articles or studies with any kind of data, normal distributions are a part of it because of something called confidence intervals. If you ever look at an election cycle, you'll see where they talk about, the polling percentage of this person is 52% plus or minus 3%. That's because of the normal distribution. You have to understand the normal distribution to be able to get to understand what those numbers mean.
okay.
Yeah. So it legitimately, you're just not aware of the things that you would need this for yet. But I'm glad that you're asking that question. I will say this for sure. You will use this way more, Madison. You will use this way more. Huh?
Me?
Never mind.
No, you're just talking about you being distracted.
Never.
Never. You'll use this way more than you would use most of Algebra 2. Okay. So, just a couple minutes before we wrap up. Here, a relative frequency histogram not only gives the normal curve its shape, it also provides information regarding the percent of data that lie between each standard deviation and normal curve. That's what the empirical rule is all about, what we're going to discover with this. So use the histograms from getting started to estimate the percent of data between each standard deviation. Write each percent in the appropriate space on the graphs of the normal curves in the previous activity and explain your reasoning. So, what they're talking about here is to look at this space and identify what percent of data would fit inside of this space. Well, how are we going to figure that out?
Oh, would it be 0.4?
So, I'm asking how would we figure this out? You don't know the answer yet, because we're talking about, please understand, we're talking about the relative frequency, the percent of data underneath the curve. We're not talking about the standard deviations. But notice, between 10 and 10.5 would be right here. So how can I figure out the total amount of data below the curve there? What percent is there?
Wouldn't we go on the y-axis and calculate?
So you'd have to look at the y-axis. Notice, if it's in between, it's a 0.09 here. It's either going to hit a line or it's going to be or it's going to be in the middle. So this is 0.9. What is this one?
0.8.
0.8. 0.7. So 0.9, 0.8, 0.7 gives me 0.24. And then both of these are 0.05.
Wait, where do you get 0.24 from?
So I added these up. 0.09 plus 0.08 plus
Oh, okay.
0.07 plus
You could've just said that.
0.055 or 5 twice. And so between 0 and 10.5 or 10 and 10.5, what percent of the data is there? Because there's two of those bars right there. That's it. Yeah. So what percent is underneath that curve?
0.24.
No,
Sorry.
so you 29 times 2?
Y'all just calling stuff out.
Oh, good. Calculate,
There's
baby.
this weird thing called a calculator.
0.58.
0.017 or 0.17, 0.24 plus 0.1 is 0.34.
Yeah. Where you get one at?
Exactly.
We're doubling this because there's two of those columns. So here is a 0.34 or 34% of the data is there.
Mr. Kenny, does medicine make your brain hurt?
Huh?
Man.
Every now and then.
Yeah.
So, yeah, if we come back to this, weirdly enough, Madison, you can, instead of getting frustrated, pick up a calculator and add those things together.
But it's kind of fun to do it in your head.
Well, if you're getting frustrated about it, it ain't fun anymore.
Yeah, it is kind of fun though.
You're gonna drive me crazy. Cocoa Puffs. All right, so we'll wrap up that lesson hopefully tomorrow. Don't forget lesson 1, practice numbers 1 and 2. Those are due tomorrow. Please note, right, it's just the practice, numbers 1 and 2, but number 2 finishes on M5-18. There's parts D and E on the back side of that page.
So we do that whole.
No, this is the same one I assigned yesterday. Yes,
We gotta do
ma'am.
that whole.
Say it one more
We
time.
gotta do the whole.
Practice. Just the practice, numbers 1 and 2. Yes. Yes. Just put it on my desk.
The bottle gonna drop 1,000 times.
Golly, y'all killing me.